So, hello everyone. Good afternoon. We are going to start another Seminários de Controle. We are very happy to have you here for this presentation that will be given by Professor Daniel Ferreira Coutinho. The presentation is entitled A Collection of Results on the State Estimation of Chemical and Biochemical Processes based on Semi-Definite Programming. I am going to present Professor Daniel, and I will present him giving his bio, a short bio. Daniel received his Master of Sciences and Doctor of Sciences degrees in Electrical Engineering from Universidade Federal de Santa Catarina, here in Brazil, in 1993 and 2003, respectively. In 2001, he was a visiting scholar at the University of Newcastle, Australia. And from 1998 to 2010, he was with the Faculty of Engineering at PUC, Rio Grande do Sul. In 2008 and 2018, he spent sabbatical on leave at the Université de Mons and Université Libre de Bruxelles, respectively. In 2010, he joined the Department of Automation and Systems of Universidade de Santa Catarina, where he is currently an associate professor. He is a senior member of the Institute of Electrical and Electronic Engineers, as well as an associate editor of the IMA Journal of Mathematical Control and Information and International Journal of Robust and Nonlinear Control. His researches include robust control, filtering, and estimation of polynomial and rational nonlinear systems, descriptor systems, time delay systems, and switched systems with applications in robotics, bioprocess control, power electronics, and power systems. In the last few years, having a collaboration between our group here, LADES, and the group of Professor Daniel and TNU. So it is a great pleasure to be working together with Daniel and to have him here for this presentation. So Daniel, thank you very much. I'm going to pass the word to you.
Okay, thank you, Maurizio. Thanks for the word. I think you have someone is with
Yes,
open microphone. But
I will.
okay, thank you, Algemiro. It's really nice to be here to present. A good day to everyone. So the presentation. Just a moment. Okay. So the presentation entitled A Collection of Results on the State Estimation of a Chemical and Biochemical Process based on Semi-Definite Programming. I am a professor, associate professor at the Federal University of Santa Catarina since 2010, and I'll try to show some of my research related to process control. The summary of the presentation, I will start with giving a short introduction. Then I will try to motivate the state estimation problem. I will jump to try to more to formalize the problem of interest. I use the concept of input state stability to show the convergence properties of the state estimator. Introduce briefly the mathematical tool that I use to solve the estimation problem. It's based on semi-definite programming. Then I will show three different ways of using semi-definite programming to design state observers. First one is one used in the estimation of bioprocess. It's called a hybrid observer. Hybrid in the sense of combining two different observers. One a classical asymptotic observer for bioprocess, and another a classical exponential observer. I will give more details when I introduce these observers. Then I will show a complete different approach to design the observer based on sliding mode. This is a particular example of a second-order sliding mode observer called the super twisting, and applied to photobioreactors. And finally, you show that, this approach can also be used to solve problems in distributed parameter systems. Okay, then I will end the presentation and show from where you can find more information about these three observer designs. So the measurements are, I would say, is a primary has important primary importance for monitoring and control of chemical and biochemical process. So, for example, to ensure robustness and performance on continuous production of a chemical or biochemical product, we have to rely on the use of control techniques, and sometimes we are blocked by the absence of a sensor for some key variables. You show that, for example, in the bioprocess, we have to estimate some abstract variables which represent something that is not directly measurable. Then you have to use a kind of observer to estimate these values. Then to alleviate this problem, we have to rely on observers or software sensors, which are depending on the research community receives this fancy name, software sensor. But this is a appealing alternative to use costly online hardware probes. Sometimes the probes for some specific measurements is very expensive, or even does not exist. But here I will try to approach this using a model-based observer. So you have the knowledge of the model, the nonlinear, in general, nonlinear equations, and then I try to design the observer, giving some properties, not only using linearized model. So other thing, I will be sometimes quite technical here in my presentation, but I will try to summarize and not giving too many technical details. So I will start here, given a motivation. I use this example because we have some experimental data. So the idea here is to estimate some variables in a microalgal culture, which can microalgal culture, microalgae, can be used in several applications with some very expensive applications. And here I will try to show some estimation techniques to predict some behavior of the microalgae growing in the culture, which will be shown here in the photobioreactor at a lab scale. And I use, as my approach are based on model-based approach, I use the model proposed by Troop in 1968, so many years ago, which describes the ability of the microalgae to store nutrients and having a decoupling between substrate uptake and biomass growth. For this, Droop introduced a kind of abstract variable. He called it a quota. So this means how many nutrient storage in the intracellular level are inside the cell. So this try to describe how the cell may grow in the media. So the model consists of three straight biomass, here X, capital S is the substrate, the feed, it provides the energy to grow the microalgae, and here is the quota. So the model is relatively simple. We have here two two reaction rates. The first one is the substrate uptake here, rho ds. Then you have here the micro G growth rate, which depends on the level of quota. So here the idea is that we have a minimal level of nutrients inside the cell, such that the cell can reproduce itself. Otherwise, it stops the growth. So you have to, this quota is very, as a key variable, you have to keep the quota, which depends on the substrate, a certain level, above certain level, to have the growing of the microalgae. The results that the practical results that I show is based on a lab scale experiment. It's a 13 liters flat panel photobioreactor. It's illuminated from one side by 6 fluorescent tubes placed vertically. I'll show the picture next slide. And we have some measurements. So, where is the picture here? So you have here the flat panel, 13 liters. You have some measurements and some equipment to make the measurements. So in this setting, we have the 3 online sensor: temperature, biomass, and the nitrate concentration, the substrate concentration, and one offline in which we try to estimate internal quota using taking a sample here and measuring some of that. So this is not very, the sampling rate here is very low for this offline measurement. So the idea is to, from the model, which is a model, no model, but with some uncertainty, because one problem here is to estimate with a certain accuracy that this to the half saturation factor here, Ks, and the maximal reaction rate, O and me. So these are difficult to measure. So I assume that I know partially the model. I have some uncertainty in the model. The observer will be a copy of the model dynamics, of the nominal model dynamics, assuming that the parameters are perfectly null. I have an output injection term. The idea is to correct this mismatch between the real model and my model used for the observer. Then to evaluate the convergence, I use in general the error dynamics. So it's the difference between these two dynamics here. So I evaluate the error dynamics. Here the observer gain is this L here, the matrix L. This you try to ensure input state stability for the error system. What I mean by input state stability. The idea, for example, when I have a mismatch between these two models, I am not able to make the error converge to 0, but the idea would be make the error converge to a very small region, very small as possible region, or so the error will orbitate around the the orange of of this state space error dynamics. Okay, so let's make the error as small as possible. In other words, here I have some examples of this setting. So in blue here are the real values of the measurable values of the in the top I have the biomass, here the substrate, and the third the quota, intracellular quota of the microalgae. So here in green are several estimations, but this depends. I have used here different values of the parameter uncertainties, and I saw that for one particular one, the error is 0, but for the other ones, the error is as small as possible. And here is the offline, so I show that the quota is more or less well estimated using this approach. So the input state stability approach to try to ensure that the error is in view of this mismatch between the models, from mismatch between reality and my model. I try to make the error as small as possible. What I have used so to make this design. The idea here, I have a nonlinear system which describes the process. I have the measurement, nonlinearities, and possibly disturbance. I assume that measurable inputs, non-measurable inputs, and this model uncertainty are bound to certain sets. My state observer will be the nominal version of this model. What I mean by nominal version is the the model with things that I know. For example, I don't know this input, so I don't use here in the state observer. And I consider the value of theta, which is the deviation around the nominal value, as 0 here. So I have a model of the reality. So I will construct the aerodynamics, just to make this dynamics minus this one. I have the aero, and my idea here is try to make the error as small as possible in view of the, because I have here this uncertain part, which is not is the mismatch between the reality and my model. Is makes the error not 0, but I will try to design the gain here L to make the error as small as possible. So to design, I use the idea of input state stability. Basically, I will try to determine a Lyapunov function candidate, which makes this condition true. So the time derivative of the Lyapunov function is smaller than a certain scalar between 0 and 1 times the uncertainties or the unknown inputs minus the Lyapunov function. If this condition is satisfied, I can show that this region here, that the error trajectory are always inside this region. And the idea is try to use an optimization problem to determine the gain L such that this region here is as small as possible, which is a region confining all the error trajectories. Okay, so this is the idea for the observer design. To design the observer, I use the semi-definite programming. So I just briefly hint 2 or 3 slides to try to show for the ones that are unaware of this technique. So basically, semi-definite programming is a particular class of convex optimization problems. So the idea is I have a cost function, which is linear with respect to the decision variables. And the constraints are positive semi-definite matrix constraints. So the idea is to use this to try to determine the Lyapunov function subject to these constraints in terms of matrix inequality. I can say that a semi-definite problem can be cast in this way. So minimization of psi here. So psi are the decision variables. So supposing I have m decision variables. So the cost function is C transpose psi. So C is given, subject to a set of matrix inequalities. These matrix inequalities belongs to the class of semi-definite matrix constraints. So they are symmetric functions, affine functions of the decision variables. I have a set of conditions like this. So this is the problem that I'm trying to solve. So the problem is to for example, to transform these conditions and make this like this to solve numerically and determine the variables that of interest. And when we have only this feasibility condition here, we call this linear matrix inequalities. Otherwise, I can say a semi-definite programming or a convex optimization problem. This particularly this approach has very important effect that the optimization cost function is linear and the constraints are affine on decision variables. brings very important behaviors, characteristics that are very helpful here to deal with constraints which can be, for example, depending on some parameters, which will be the case when designing a state observer here, assuming that the error is not perfectly known. Then, for example, if I have two solutions for two different set of solutions for the same constraints, for example, the constraints are satisfied for a vector, a decision variable psi, and a vector sigma here, I can show that the convex combination of these two possible solutions are also a solution. So this particular characteristic is very important because imagine if I have to test this matrix inequalities here for a set of values of this parameter theta, which represents the uncertainty. It has an infinite dimensional problem, but if I assume that this parameter belongs to has a lower and upper bound, I can check these conditions for all possible values of theta, only checking at the extremum values. Okay, this is will be make possible to solve our problem. So continue here. Other thing, but I have to how to transform this matrix inequalities into my problem. My problem is related to the sign of scalar functions, Lyapunov candidate or the time derivative of the Lyapunov function. And they are in general quadratic form of this type here. So zeta here is a vector. If I try to, for example, to check if the sign of this condition is larger or equal to 0, I can only check if this matrix here is definitely positive. So I can, using this matrix inequality, determine the sign of this quadratic form. So this is the basic idea. For example, if I try in a case, a linear case, try to find a matrix P such that the time derivative of the Lyapunov function is strictly positive. So here in general, the solver solves here non-strictly conditions. But if I try to solve in strict condition, I can just add a very small positive scalar. So this, if this is larger or equal to 0, then the time derivative, which is 2 x transpose PA x, is smaller than 0. So this is basically strictly negative condition. Note that my variable here is the matrix P, but the solvers in general consider this kind of version. So this is called the standard form. The solver solve this form, but we can transform from this matrix condition to this scalar condition. Here the decision variable are the elements of the matrix P, and here the decision variables are psi1, psi2, and psi3. But I can transform the one to the other using very easily. But for our luck, there are specialized solvers which make these transformations. It's more easy than I showed that. And the matrix inequalities solvers have appeared in the early 90s. So in the beginning, we have this difficulty in transforming conditions like this, which appears when I'm modeling the problem, for conditions like this here, which I call the general form, which are used by the solver. But nowadays, there are specialized packages which transform from one version to another. So they are kind of transparent to the user, which call the parsers. So, for example, there's one is called YAUMIP, and the other one from Stanford is the CVX. So these two are the main parsers that I use and know. I particularly use the YAUMIP. Was the first one to appear. And there are several different solvers. For example, there's one called Seduni, another one SDP3, which are free, but they are based on MATLAB, so we need MATLAB to solve. But anyway, they are able to solve very efficiently problems like this. So returning to the observers, I introduced the first observer, which is called we call it the H-infinity hybrid observer. So this is a result of a collaboration with a colleague, speaking in French, Université Libre de Bruxelles, is from the French-speaking part of Brussels. It's a funny country. And this tried to combine a classical asymptotic observer. This was developed in the 90s. The beginning, in fact, in the late 80s, it was developed by two Belgian researchers, the Basta and Duchamp, which try to avoid to use the model to make the estimation of the states, and a nonlinear Leuenberg-like observer, so an observer like this one, similar with this structure in C. So you have the nonlinearity. So returning to the hybrid observer. So the idea, the asymptotic observer, they using a kind of a model transformation, try to make it decouple the measurable part from the non-measurable part, and for a particular class of bioreactors, they are able to show that this unmeasured part can be made independent of the reaction rates, which are the most difficult parameters to determine. So I mean by the reaction rate, so the expression here, even they are unknown. So there are several different reaction rate expressions, which are more indicated per certain cases, and also it's difficult to estimate these parameters here. So the reaction rates are the major source of uncertainty in the model of a bioprocess. So the idea of the Duchamp in Bastin was try to make try to find a model which is independent of this reaction rates. So you show how they did this. But the problem of the asymptotic observer that the convergence depends on the dilution rate. So it's an open loop observer. So as the model is relatively accurate, because they are not reliant on the reaction rates, but the convergence depends on the parameters of the model and also on the dilution rate. For example, is it possible to use this kind of observer for a batch process? So one for fed batch or continuous operation of a bioreactor. On the other hand, there are several exponential observer. I mean exponential observer. So observer in which we can show certain exponential decay rates for the error dynamics. For example, we have the extended Kalman filter, the unextended Kalman filter, extended Leuenberger observer, or even the receding horizon observer. So they exhibit some good convergence properties, but they depend heavily on the model accuracy. If the model is not perfect, so you have always a certain level of error. And this is mainly due to the kinetic part of the bioreactor. So the idea of the hybrid observer is try to run the two observers in parallel and using a kind of a scheduling parameter which measure the model accuracy. So if the model accuracy, I use more the asymptotic observer than the exponential observer. Otherwise, if I try to measure and see that the model is good, I try to use the estimation from the exponential observer. So if we try to mix these two observers. One has some issues in the convergence, another one some issues with respect to uncertainty. I will try to combine these two observers in try to use them to build a better estimate than a single one. So now I recall some bioreactor model, macroscopic model. So this model structure was proposed also for Bastien in Dosha in 1990. And the microscope model describes some of the main phenomena occurring in the bioreactor. So the components are substrates, metabolites, and products of interest. For example, ethanol depends on the fermentation process, and maybe oxygen, production of oxygen and carbon dioxide, just for example. So basically, we are able to construct the bioreactor process in these three parts here. We have one which relates the reaction rate occurring in the bioprocess. Here is a matrix of a stoichiometric coefficients. So here the main source of uncertainty is the expression of the reaction rates. Here this is the dilution rate. Here's the state. The state in general is biomass, substrate, other metabolites and byproducts. And we have an input here, U, which corresponds, for example, the feed flow rate to the culture, and also gaseous outflow rates or feed. So the external sources that are here in this variable U. So the idea for the asymptotic observer is try to divide the model in two parts. There are certain conditions to be able to make this transformation. So you say that the measurable part of the state is x1 and x2 is the part of the state which I want to estimate. And if I have certain conditions over this stoichiometric matrix K, is this a rank condition, I am able to use a kind of a state space transformation and rewrite this dynamics here in terms of a measurable part plus this dynamics here in terms of this auxiliary variable z, which is a function of x1, which is measurable, and x2 is the part that I want to estimate. So this transformation yields this model representation, this state space realization for the bioprocess. So here this model here depends on the reaction rate vector, but this is measurable. And the non-measurable part does not depend on this main source of conservatives, of the main source of uncertainty. So this the good the good point of this observer. But if you note here in this observer, the the convergence of this observer, we will see which will depend on the value of the dilution rate, which tends to if the dilution rate is very small or even if it goes to zero, we lose the convergence properties of the observer. So this is a very bad point. So if we need a certain dilution rate to be able to have a good estimation. So basically the observer is just a copy of this dynamics of Z, and the estimation is just we have to use a kind of a pseudo inverse of A2 to obtain here the estimation for X2. So this is the asymptotic observer. This is the final expression for the aerodynamics of the asymptotic observer. You see that it depends on the dilution rate, the time constant of the observer, the estimation of aerodynamics. Then we go now to introduce the other kind of observer. It's called the exponential observer. I put here the robust because we are admitting uncertainty in the model. So we have here, I used, for this case, the same transformer model here, but we have output injection terms here, which will try to impose a certain convergence rate to the observer. So this will make not so dependent on the dilution rate, the observability properties of this observer. So basically, it's the same asymptotic observer with these output injection terms, which I have to design the maps L1 and LZ. So the idea to design the observer gain is to compute, determine the aerodynamics. Here is the aerodynamics. And design this to have some certain properties. The idea here is to minimize the size of the aero trajectories. Despite the model uncertainty, I suppose that I have model uncertainty here in the on the reaction rate. So here's the reality, here is my estimation of the reality. So we have a mismatch between these two cases. So the idea I use here a kind of as these reaction rates are a rational function of the states in general, in particular case for bioreactors. This is here, this expression of reaction rates are very common. So in general, they are rational function of the states. So for this class of systems, we can use a kind of nonlinear polynomial description for the model. I obtain a model like this with an additional constraint, and I'm able to design the observer and try to make the aerodynamics as the aero trajectory as small as possible. So to this end, I transform this problem using input state stability, and here I try to estimate the size of the estimation region, and here I have the conditions to make the time derivative negative. So if these conditions are satisfied, I'm able to design the observer gain, and provide a bound on the size of the estimation error. Other point, so to merge these two observers, I have a kind of a scheduling variable, we call here delta, which belongs between 0 and 1. So the stream value here, 0, means that the model is very bad, so I have to rely on the asymptotic observer. And 1 means that the model is very good, so I can rely on the exponential observer. When so the idea I have these two estimations. So I have the estimation of Z and the estimation of the asymptotic observer and the exponential observer, and I try to combine. Here, the estimation, when delta is equal to 1, I use the estimation of the exponential observer. When delta is equal to 0, I use the value, the measurable part, so the asymptotic observer. So how I construct this scheduling variable? Here I use very simple idea. The idea is to have a metric of the estimation error variance. So I use here the integral from time 1 to time 2 of this matrix of the error, the size of the error, and try to make this determine if I use one value or another. So delta here goes from 0 to 1. Here this time here, theta minimum here, t minimum here, means I wait. In the beginning, the asymptotic observer has a very large error because then I may start with a bad initialization conditions, initial conditions, and I weight the, the estimation converse to make it closer to the real value, then I try to measure the size of the error. If the size of the error is very large, so I give more importance to the asymptotic observer. If the error is relatively small, I use exponential observer. So to illustrate this problem, I consider here a first case study to show here. Is an animal cell culture. We have three stages: substrate, lactate, and biomass, and two reaction rates. So these are a little bit different from the photobioreactor, but as I said, there are in general polynomial, a rational function of the states. So I suppose uncertainty on the values of the maximum reaction rates, mu1 and mu2, and the value of the Kr, Kl, and Kf. So here I have the several simulations. I try to show here in the first is the biomass for the classical extended Leuenberg observed. So this I use a result from the literature, and the green is the asymptotic observer. So I show that the extended Leuenberg observer depend on the size of the uncertainty may provide very bad estimations from the real value. The real value is this in blue. Solid blue here is this real value. So in green here is the asymptotic observer results. It's better than, depending on the accuracy of the model, is better than the estimation provided by the classical extended Leuenberg observer. And here, on the right top here, and here I have a classical hybrid observer combining these two observers. So you see that the exponential observer, the error from the extended Leuenberg observer here is smaller than in this case. It's closer to the asymptotic observer. I have again when considering this combination of these two different observers. Here below, here in the bottom, in the left-hand side, I have the robust exponential observer by itself. I notice that the error is smaller than in the extended Leuenberg observer. I provide a better stage because I'm designing the observer gain to minimize the error. Okay, so the idea is this. So I'm able to have a better estimation compared, for example, to the extended Leuenberg observer or the classical hybrid observer, which is a combination of these two bad observers. And now, if I use the combination of this robust observer and in green the asymptotic observer, we see that they are able to even minimize the error. Here, the error. I have here 50 runs for different setting of a parameter. I have uncertainty of 20, 50% on the parameters here in this 5 parameters. I have just here 50 runs. So we see that the error is much smaller than in the other case. And I am able, if the combination of the asymptotic observer, the problem of the asymptotic observer provides a very good estimation because the observer does not rely on the value of this reaction rates. Then the estimation it has a small error compared to the reality. But the problem is the convergence rate of the asymptotic observer. Here I starting from very close initial conditions, but if I start with a bad initialization condition, so the asymptotic observer will take a long time to converge to the real value, which is not the case from the robust observer, which converges very fast to the reality, but I have the error because of the model mismatch. So this was the first class of observers. Now I go for a very different strategy, which is based on sliding mode. Sliding mode has the property of providing, depending on some matching conditions, to provide a zero error, convergence error, despite model uncertainty. But it's not always the case. Okay? Depends on the application. If these matching conditions are not satisfied, so we have a kind of behavior similar to this. Not similar. We see that the super twisting observer provides a better estimation than this robust estimation. And this is a little bit more recent work of mine, which I made in collaboration with Alejandro Vargas from Mexico and Professor Van Volver from University of Mons in Belgium. And the contribution here, I did not propose this super twist algorithm. This was proposed in 1993 by Levin, and further investigated and used a kind of Lyapunov description to provide convergence properties for the super twisting observer. We used the approach of Morena, another Mexican guy, and here we use the idea is try to design some tuning parameters, which in the literature in the past they use some kind of ad hoc kind of a try and error approach to tune this some parameters of this super twisting algorithm. So the super twisting algorithm is applicable to a very particular class of system. Here I'm using a very simple model with only two states, but this can be extended to two sets of states. So x1 and x2. x1 is measurable, and x2 I would like to estimate. So here we have this function v has to be positive, maybe uncertain between a lower and upper bound. H1, this output injection term is measurable, and this is no measurable. The same here in the second part of the system. And we are measuring x1. So the idea is use an observer, which is a copy of the model. So here you have the estimation. Here B can be estimated precisely because we measure Y and U. This is also precisely estimated. This is not precisely estimated because it's just an estimation of this term. So the difference between F1 and F1 hat is not zero. And we have here an additional term to try to improve the convergence properties of this observer. The difference between the exponential observer, that here this is a discontinuous function of the states in general, is a kind of the sine function, which is used here in this function phi1. And for the second part of the system is also a copy of the system. This is a perfect copy of the second part of the system dynamics, and this is an estimation of F2, and plus the correction term. We have here a different function of the estimation error. So x1 tilde is the difference between the estimation and the reality. So this super twisting observer has some conditions to use. That this function psi1 and psi2 are not totally free, but are not totally no. So we have to choose between several candidates. Functions psi1 and psi2 satisfying these two conditions. So the first one is that the partial derivative of this function is also positive, and psi2 is a function of the psi1 and its partial time derivative, partial derivative, not time derivative. Sorry. And in general, the super twist algorithm was proposed in the middle of the beginning of the 2000, the middle of 2000, 2005, more or less, is a general expression for the super twisting algorithm. So the function psi1 is defined like this, and psi2 is obtained by this expression. So psi1, so we have a kind of a metric of the size of the error multiplied by the sign of the error. So just to illustrate, we define P1, K1, and K2 appropriately. We can recover the first algorithm of a classical super twist algorithm, and also we are able to recover the high gain observer proposed by Khalil 20 years ago, more or less, using the same strategy here. So here in this work, we consider the classical super twisting algorithm. So the function psi1 is a metric of the error, the difference between the estimation and the measurable part, times the sign of this error. And psi2 results using this property here results in this condition. Now I will define the estimation error vector and have an estimation error dynamics. And to provide the design conditions, I use another states transformation. This was proposed by Javier Moreno in more or less 10 years ago, which we consider as the states. The psi1 would be a state inside instead of the tilde x1. And the second part of the state is the same second part here. So we modify this first representation. This is a kind of nonlinear transformation similarity called general diffeomorphism, which is a nonlinear transformation. Using this nonlinear transformation, we are able to describe the system in this form. Here is the time derivative, is the partial derivative of psi1, which we know is positive. We have this matrix here, which depends on the errors between the reality and my estimation. The parameter b, which is unknown, but I know the lower bound and upper bound. And here is the gain to be designed. So the idea is to, using this representation and the concept of input state stability, try to design this gain L. This gain L are the key problem in the original approach to use this algorithm that we'll try to solve here using this more mathematical, more numerically obtained using an optimization problem. I would say that if the model satisfies these conditions, some matching conditions, the error is guaranteed to go to 0 in finite time. But if this mismatch here does not satisfy certain matching conditions, so we guarantee that the error is bounded, so similar to the exponential observer. So here are the design conditions. I also provide a bound on the convergence rate and on the convergence time. It's not possible with the other approach. Then I will try to use this in the same first problem, my motivation problem. And my presentation is becoming too long. I'll try to speed up a little bit. Here, I try to estimate the quota from the model, the Druck model. But here, differently, to be less depending on the reaction rates, I will separate the system in two parts. One related to the substrate and the uptake rate as states, and the other one, biomass and the growth rate. So the idea, I suppose that I measure S and try to estimate O, which is my key issue in terms of robustness. And the second one, I estimate X. I suppose I measure the biomass and try to estimate the growth rate. And use this structure are similar to the one that I presented before to use in the super twist algorithm. So I use two observers here, and the quota will be estimated from X hat, S hat, whole hat, and me hat. Quite easily. Here are the results. You suppose a very large level of uncertainties and also a noise measurement. So here in blue are the real values, and in black are the estimation. Here the estimation is noisy because of the noise. We can improve this estimation using a kind of a filter, so filtering the output. But note that I'm considering similar uncertainties to the first case, and I have a much better estimation using this switched observer. But the problem here that I have a kind of a noise estimation, a noisy estimation. I can improve this. These are in the original paper using a filter, so I can have a much better estimation compared to the first observer that I show here. So to finalize the presentation, I can use also the Semidefinite Programming to estimate the states of systems described by partial differential equations. For example, here in the exothermic tubular reactor, I have here these two state space equations. First one here is the concentration of the main compound, and T is the temperature. So I have this model with certain boundary condition and initial conditions. The idea is to try to design an observer, for example, assuming that I'm measuring the temperature and try to estimate the compound concentration. Instead of only boundary observation, I suppose that I have distributed along the spatial variable a certain number of sensors, which provides kind of a pointwise measurement. So the idea is to use these several distributed pointwise measurements to estimate the concentration. So we can use a similar ideas here. For example, suppose that observer is a copy of the system plus a correction term. It's a little bit more involved because this is not a matrix, but a function that I have, a functional that I have to design. And I have here the boundary conditions and the initial conditions for the observer. Then using the aerodynamics, I try to use a kind of a Lyapunov approach to show convergence properties. Here the Lyapunov function is not a function, but a functional. We're dealing with an infinite dimensional space. And I suppose that nonlinearities belongs to a certain class of nonlinearities, which I can apply the differential mean value theorem to deal with nonlinearities. Then determining the time derivative of the Lyapunov function, and to show that this is semi-definite negative, I can transform this an LMI problem. So if I find solution for this LMI problem, I have a solution for my observer, and I show that this observer has exponential properties. Going here just to exemplify, we consider here some values taken from a paper from Denis Duchamp, which analyze the observer using proper orthogonal decomposition. Here I'm using not an approximate observer, but an observer using the partial differential equations. And here are the results. Here, it's a complicated because it's distributed parameter system. So here is the partial variable. Here's the concentration. Here's the temperature, and here's the spatial value. The time is the third index here is in this different curve. So here T1 represents the initial time. T2 is 0.072, T3 0.1622, and T4 is 1.4. So it's the end for us. So I start, for example, in red are the real values, and in blue are the estimations. When I start, the initial condition of the system is this in red, and the initial condition of the observer is very far, so the error is very big in the beginning. In the second time instant, in 0.072 seconds, here T2 is this in red, the real value, and in blue is the estimation, is much closer than before. So the observer is very fast. And T3 is 0.1622 seconds. The real value in the estimation are almost the same. And then T4, the error is practically zero, so the estimation is practically equal along all the spatial domain. So concluding this, this three talks, which I try to show three different observer designs, completely very different observer, but all in common. I'm using semi-definite programming to determine the tuning parameters of those observers. They are based on these three journal papers, and this one is the more recent one. This is from this year. This result. We are now improving, so now we are using here adding extra degree of freedom. I'm supposing here that I have a matrix P here in the middle, and this matrix is a function of the spatial domain. So it provides much better results than this one. But this is still under finding writing. So just a couple of days ago, we just submitted for evaluation a paper. So I complete my presentation, so I will stop here to share my screen. So thank you for everyone. Please, I'm open for questions.
Thank you very much, Daniel. Thank you for the nice presentation. You have shown us a collection of results, as you said, your collaboration with this group especially from the group from Belgium, I suppose.
Yeah.
And I think some people are particularly interested in bioreactors, and so these results of the algae bioreactor. Last year we had a visit from Professor Nadi Bar, and he was interested in developing a collaboration that included control and state estimation, but due to the pandemic, it had to be stopped. But maybe it would be. He was supposed to be here today, but I think he's not.
Okay.
Of course, other applications could be given. So we are open for questions. Professor Daniel warned me that he has only around 15 minutes more because he has another appointment. So please, I would like to invite you to make questions, comments to Professor Daniel. Ajimiro has raised his hand, so I will pass the word to Professor Ajimiro.
Okay. Congratulations on the presentation, Daniel. It's very nice result that you have shown to all this combination of observers. I have a question regarding to the hybrid observer that you present there.
Yes.
Related to the scheduling variable that you have created. It's something like a Gaussian function that you use for this variable.
Yes.
And there is a tuning parameter there. I think there is this T min. the
Yes.
minimum time to
Yeah,
this.
the function of this minimum time is the following. If we start from very bad initial conditions, so the error is very large, so we just rely on the asymptotic observer and wait a little bit to try to measure this kind of a Gaussian error to have an idea if I continues with the asymptotic observer or switch to the exponential observer.
Yes, it depends on the
Yes,
measure
in
of
the
the
size
error.
it depends. We have
Yeah.
to here in this paper.
But how
We
sensible
different versions.
how sensible is the scheduling procedure based on this parameter, this time parameter?
Price depends on the application. So we have to make some tests to try to estimate the minimum time that you have to consider to start to make this judgment of the model accuracy. Okay.
Okay.
So the other thing that the parameter the scheduling variable may be quite sensible to change. So jump to one to another very fastly. So this is not desirable. So this is there is a second parameter which is, let me see, which is the alpha parameter here. So we have two tuning parameters, the alpha and this the minimum time. So the minimum time using some running some experimental tests, we're able to estimate this value. But the alpha gives me how sensible is the scheduling variable to error in the dynamics. Okay, so this I have to be more careful when the alpha variable is more sensible.
Okay.
Okay.
Yeah.
But this is a kind of ad hoc solution.
Yeah.
There
Many
is
people
no
has some parameters to
very
turn in.
precise guideline to choose alpha and theta.
Sure. Another question is regarding to the composition that you made in the model, the estimator. That you create two sets of equations to separate the estimators, but I'm not quite sure if I understood that separation, because you still have the biomass concentration that make the couple of between those sets of equations. How it works?
We have basically two observers. Okay, the two observers
Yes.
use the same state space representation. Okay, then the estimation we are running in parallel the two observers. Okay, the two observers are running in parallel.
Okay.
The estimation that I consider is a combination of the two based on this scheduling parameter. If my scheduling parameter indicates that the model is precise, I basically use the exponential observer. If the value is smaller than 1 tends to 0, so it's basically the asymptotic observer. It's a kind of a convex combination of these two estimations. Okay.
No, I mean that the last part of presentation, when you separate, when you separate the model of not model.
I'll put the presentation here. You may try to point me to me that I may provide a better explanation.
Yeah, we have
to
two
you.
sets of equations for the estimators. One is for the substrates, and the other one is for the biomass.
Okay. This is in the super-twisting.
Yeah, I think in super-twisting, yeah. You have two sets of equations for the estimator. Two
estimators.
Yeah, this way, this point.
Okay.
Yeah, and how you combine it? Because, for example, the first estimation for the uptake rate estimator, you need the biomass concentration. How you use the measurement for that? Or?
Yes, because I suppose that the substrate and the biomass are measurable.
Okay, both are measured, but the substrate and biomass. Okay.
So the reaction rates here are not measurable. Are partially no, the expressions. And I try to estimate these reaction rates instead of reconstructing from the model.
Okay.
and I estimate the quota from here. So I have estimation of rho, estimation of me, and estimation of Q.
Okay.
This is
The
a
key
kind
idea
of a
is to have
asymptotic observer
both.
at the end.
Yeah, I understood now. The key idea is to have both measurements of the substrate
Yes.
and biomass concentrations. All right, that's fine.
So I need more measurements here, but the estimation is much better. Just to illustrate, if I filter the measurements, I'm able to have a very good estimations. So here, using a filter, I can have a much better. The error is quite small. I'm using very large uncertainties here, and even though I'm able to guarantee that the error is almost zero. Okay, the performance is much better than the first observer, but I need more measurements, and I have this issue related to the if the measurements are noise, or this may make not very good. But if here there is no filter in the measurements, but I'm adding a filter, a simple filter to the measurements, a first order system, for example, I'm able to have much better estimation. And here is the estimation of quota.
Okay.
Okay.
That's good. My last question is regarding to the parameters of your model, for even mainly for the exponential observer when you use the hybrid observer, because in your presentation you did not mention about the parameter estimation, only the state estimation. When
Yes.
you combine both parameter and state estimation, you think this will improve this hybrid observer?
Yeah, but it's more or less what I done here in the super twisting, because the rho, which is not a state in the original model, I'm estimating his value. The original model is in the beginning. Is here the original model, okay? X, S, and Q, and I have this function here. Instead of estimating this, instead of using this function construct from the identification of Ks and rho b, I'm trying to estimate this function.
Yes,
Okay.
work as a
so
parameter.
this is a kind of combination, but obviously I can use, for example, an adaptive observer, which I run in, for example, in parallel, and a kind of recursive identification. I try to improve these values here to improve the estimation. And as I'm using, for example, as I'm using a kind of a robust approach, I may think and try to use a 2 layers observer. The first layer is the robust observer, which makes possible which I designed the observer gain, not for a fixed observer gain, but for observer gain plus some uncertainty. And this variation around the observer gain, I may design using an upper layer, for example, using an minimum squares, something like this, to better estimate these parameters and try, with the time, try to improve my estimation. But this is also possible.
All right, thank you very much.
Okay.
Thank you, Ajimiru. Well, I am reading some comments here. Professor Johannes Yask, nice presentation. Thank you for the invitation. Thank you for being here, Johannes.
Thank you.
And Marcio also agree that it's a very nice presentation. Danielle And so, well, as you said that you have other appointment, you have already given your email. I will put it again here so that anyone that has another questions may address you.
Okay, if you like, I
And
can send to you the presentation if you like. I don't know. But
yes,
you have
okay,
to.
I would like,
But
please.
okay,
Yes, we are going to also make the presentation, the recorded presentation available. So thank you very much again. It was a
thank
very
you.
nice presentation.
Thank you,
Very
Maurice,
good.
for the invitation. Thank you, Jamiro, and thank you for everyone
Uh,
to
Thank you, Daniel.
stay here at the end. Let me see how many 21.
Yeah.
Okay.
Yes, in our next presentation, I'll send the information, but it will be given by Professor Ana Fratini Filetti, that belongs to Universidade de Campinas and works with artificial intelligence and has a lot of experience with techniques and also with applications, experimental applications, and also including biochemical processes. So I will send the information to you all. Thank you very much for being
Thank
here,
you.
and
Bye.
Daniel again. See you in our next presentation.
Okay. Thank you. Bye.
Thank you. Bye, everyone.